Okay, in this video, I'm going to discuss with you the following topics. First is the stability of nonlinear system. Next, the stability theory, two-dimensional autonomous systems. The third one is the classification of the nature of the steady state. And the last one is the population dynamics of two competing systems. So let's now proceed to the first part, the stability of nonlinear systems. So from the previous video, we solved for linear systems. So on that example, we simply put the equation coefficients in a matrix format and solve for the eigenvalues of that matrix. And then from that, we can already say if the system is stable or unstable. But for nonlinear systems, it is not possible to just simply put it on a matrix format, because a matrix format can only take a linear format. So this time, our approach is linearization. Okay, so a nonlinear behaves like a linear if you get close or zoom into it. That's why linearization is possible, and this procedure works. Okay, like for example, I give you an example, a function of x sin x. So we know that sin x is a nonlinear, right? And in the graphical form, it looks like this. So it is definitely a wave, a nonlinear one. So how can we get its linear form? By using a Taylor series expansion. Okay, Taylor series expansion. Getting the first order of this expansion is getting the linear format of the nonlinear system. It works because, for example, if we will take a closer look on this sine wave, you're gonna get this view. Okay, it is not yet a perfect line, but if we iterate and take a closer and closer and closer look, you definitely will get a line. Okay, so for any nonlinear system, we can do the same. By zooming in, we get a view of a line. Mathematically, we can use the Taylor series expansion, get the first order of that expansion for the nonlinear format, or a linear format of that nonlinear system. Okay, so moving on to the next part, before I give you a much profound example, so we discuss first the stability theory, a two-dimensional autonomous system. The example that I will going to give you is a nonlinear one. So to give example for the previous topic, and also this example would be a two-dimensional. So to serve as an example for this second topic. So for stability theory, the questions that we might ask: in a steady state, what is happening around that steady state? What if we perturb that system or introduce a very small deviation on it? What will happen? Will it go back to the same steady state? Or will it go away from that steady state? So those are the questions that we ask in the stability theory. You may say that when it comes back, it is attracting, so a stable one. But when it goes out or goes away, it is unstable. For example, you have a marble and you are in a valley. Okay. So the steady state of the marble is at the bottom of the valley. Suppose you introduce or apply a force from its left to move it to the right. So the tendency is that the marble will go to the right somehow, but when the force has been exhausted, the tendency of the marble is to go back to its original state, simply because of gravity. So we can say that the steady state of the marble at the bottom of the valley is stable. Now, suppose we put the marble at the top of the hill. Okay, we apply a force from its right, expecting that the marble will move to the left. After the force has been exhausted, the question is, will the marble go back to its original state at the top of the hill? Or will it continue going down, reaching the bottom of the valley? Of course, obviously, the marble will continue to go down at the bottom of the valley because of gravity. So we can say that the original state of the marble, though it is a steady state, you can say that it is unstable. So for stability theory, we analyze those things. So what if, for example, we have nonlinear equations so for example, we have this dot of x equals to x 3 minus x minus 2y, and another function dot of y equals y times 2 minus x minus y. So for the first function, dot of x, we say it is a function of x, y. And then the second one is a function of g, x, y. Okay? So both of these functions are nonlinear. Just to give you an example from the previous topic. So I'm giving you a nonlinear functions. These are also two-dimensional because we have the combination of x and y inside a function. So the question is, how are we going to analyze its stability? So we have here the step-by-step procedure. So first, the idea here is, because it is nonlinear, we have to linearize the equations. This is the first approach. Okay, because as we already know, if everything has been linearized, we can proceed with the matrix form and then evaluation of the eigenvalues, then the analysis of the stability. So that will be our first approach, linearize the equations. So how can we do that? So we can do that by using a Taylor series expansion, or we simply use or create this Jacobian matrix. So Jacobian matrix is simply the collection of the elements of the given nonlinear functions. So for the first element, we get the partial derivative of the function with respect to x and then y. So for the next function, we also get the partial derivative with respect to x and y. Okay, so this is our Jacobian matrix. Shouldn't have this one. So this is our Jacobian matrix for the two nonlinear functions. The next thing that we will do is to determine the fixed points. So in order to do that, we set the value of x and y as 0. Then this serves as the first fixed point or critical point. Okay, so for this x and for this y. Then we substitute. If the value of x is 0, what will be the value of y? If the value of x is 0, the value of y is 2. So then we get another set of points. Then next, we do the same to the other function. We substitute the value of y as 0, and then we compute for the value of x, resulting to 3, 0. We get the third set of points. So, is there anything that we can do to get another set of points? So yes, suppose these x and y are non-zero, so we must solve for this equation, and this one. Okay, so we find the value of 3 minus x minus 2y. So we find the value of x and y from here. 2 minus x minus y equals 0. So we simply subtract this equation. So we get 1 minus y equals 0, or y equals 1. Which then, if we substitute this value of y equals 1 to any of these functions, equations, we get the value of x equals 1. So we get the fourth critical point or fixed point. So having this for critical points, we will now compute for the eigenvalues. Okay, using the Jacobian matrix. So at 0, 0, our Jacobian matrix is, you simply substitute the value of x and y to the Jacobian matrix. So our Jacobian matrix is this. So we first expand this, distribute the x and the y. So we have 3x minus x squared minus 2xy, 2y minus xy minus y squared. Okay, so we get the partial derivative of the function f with respect to x. So we get 3 minus 2x minus 2y. Okay, then the other one with respect to y, we get negative 2x. So for the other function g, partial derivative of function g with respect to x, you get negative y, and then we get 2 minus x minus 2y. So this is our Jacobian matrix for the two nonlinear equations. Now we solve for the Jacobian matrix for each critical points. At 0, 0, our Jacobian matrix is equal to 3, 0, 0, 2. Our eigenvalues are 3 and 2. Both positive means unstable. So this analysis I'll discuss on the next topic. So for now, we proceed to the next fixed point, 0, 2. So our Jacobian matrix here is equal to negative 1, 0, negative 2, negative 2. Okay, so what we get here, eigenvalues are negative 1 and negative 2. Both negative, so they are stable. At 3, 0, our Jacobian matrix is equal to negative 3, negative 6, 0, and negative 1. So from here, we get the value negative 3, negative 1. Both eigenvalues are negative, so it means it is stable. And then lastly, for fixed point 1, 1, our Jacobian matrix is equal to negative 1, negative 2, negative 1, and negative 1. So, our eigenvalues 1, and eigenvalues 2 sub 2 is equal to negative 1 plus or minus square root of 2, negative 1 plus or minus square root of 2. So 1 will result to a positive eigenvalue and 1 is a negative. So it means it is unstable. Okay, so I think we're done with this topic. So for the face portrait, it is better discussed on the next one. So it is a classification of the nature of steady state. So in general, we can predict the behavior of the solution to a linear or linearized system based on the eigenvalues of the matrix. So when we have a negative eigenvalues, the solution tend to go to 0 or a stable. For positive eigenvalues, it will cause the solution to approach infinity or it means unstable. For imaginary eigenvalues, it's leading to a spiral behavior of solutions. So eigenvalues with positive greater than 0, we have a source. We call it a source. So here it is a source wherein the arrows are coming out from the fixed point. When the eigenvalues are below 0 or the negative values, we call it a sink. So from the fixed point, the arrows are coming in to the fixed point. When our eigenvalues, when one is greater than 0 and another one is less than 0 or negative, we call it a saddle point, wherein some of the arrows are coming in and some of the arrows are coming out from the fixed point. We call it a spiral, outward or inward, when we get an eigenvalues of a complex number. So when the real part is greater than 0, it is outward spiral. And when less than 0 or negative, it is an inward spiral, like on this example. And then lastly, we call it a center when the eigenvalues are both imaginary. So the tendency of the arrows is just to go around the fixed point. So sketching the face portrait for the previous example. So we get the first fixed point lies on the 0, 0. Okay. So the other fixed point on 0, 2. The other is 0, 3. And the last one is at 1, 1. So if we will analyze the eigenvalues of 0, 0 fixed point, we get both the positive eigenvalue. So it means it is a source, and so from that fixed point, the arrows must come out. Okay, so the tendency of the arrows to come out. So for the other fixed point, let's say on 0, 2, the eigenvalues that we get are both negative, so stable. So we call it a sink. It means the arrows comes towards it. So the arrows coming towards it, coming towards it. The same goes with the fixed point 3, 0. It has a negative eigenvalues, so it is a stable and also a sink. Okay. Then lastly, for the fixed point 1, 1, we have eigenvalues of positive and negative. So since we have different signs of eigenvalues, we call it a saddle point, wherein some arrows are coming in, and some arrows are coming out. Okay. So this is the face portrait of our example. So I think we're done with this example. So for the last part, population dynamics of two competing systems. So the definition of this is a field that models the evolution of populations of plants, animals, humans over time. So in this topic, we should know about the condition of the environment. First, you must be able to create a model derived from the population and within the environment. Okay? For example, we have two species, a rabbit. No, it should be rabbits and foxes, wherein the foxes prey on the rabbits. Okay? So, let's make some assumptions. Number one, rabbits have unlimited food supply. So, there are a lot of grasses, I think carrots, um, food for the rabbit. So, it's for the rabbit. So, there are rabbit. So, we call this rabbit as X. Okay? So, this is X. So we have another species which is a fox. Let's draw a fox. Yeah, that's a fox. And name it as Y. Okay, so it preys on the rabbit. No, should be like this. Okay, so this is our first assumptions, that rabbits have unlimited food supply. Hence, if there were no foxes, their number will grow exponentially. So we put it now into equation. So suppose we have change of the rabbit over time. We have AX. So but in reality we have foxes. So the tendency of it is to decrease by a proportional xy. Then we put the coefficient here b. Okay. So this is our first equation. For the second equation, for the foxes, so our foxes will decrease okay, so our foxes will decrease when there is no rabbit. Okay, but since then there are rabbits around these foxes, so we can say that there's a tendency to increase their population with some proportional xy coefficient x k. Okay, so these are our two nonlinear equations for this model or this environment, this interaction of rabbits and foxes. So now, how can we determine the stability of this environment? So of course, since we have now these two functions and we cannot put them directly in the matrix form, we have to linearize them. Okay, but first we define some values here. So our a be equal to 4, b equals to 1, k equals to 3, and rl is equal to 6. Okay, and then we substitute these values to our equation to get our working equations. Okay, so as you remember what we have done on our previous example, after getting the nonlinear equations, this expanded form, we get the fixed points, and then the Jacobian matrix. So our Jacobian matrix for these two functions is this. So first, we compute for the partial derivative of the function x. So we get 4 minus y, then minus x. Third equation, we have 3y minus 6 plus 3x. So this is 3. Okay. So this is our Jacobian matrix for these two nonlinear equations. Next is we get the fixed points. So what would be our fixed points here? So first, okay, so we factor out x from this one. So we get x 4 minus y, and to this one we factor out y. We get 3x minus 6. So our first set of fixed point is 0, 0, setting the value of x and y as 0. And then for the other, the inside equation, so we can get here a y value of 4. And for the other equation, you get the value of x as 2. So these two will be our fixed points. So now, we will get the eigenvalues for each of these fixed points. What we're gonna do here is, and at 0, 0, it will be our Jacobian matrix. Set this as 4, 0, 0, and negative 6. So our eigenvalues here are 4 and negative 6. They have different sign, so we can say that they are unstable. Saddle point. Okay, so at 2, 4, our Jacobian matrix is equal to 0, negative 2, 12, 0. So our eigenvalues here is positive or negative 2 square root of negative 6. So from here, we have positive and negative imaginary number. So we can say that this is a center. Meaning our face portrait would be a circling one. So plotting for the face portrait, We have the first fixed point, 0, 0. Then we have 2, 4. So somewhere here. Okay. And since we have a center, so the tendency is circle around. So this is true with the relationship of rabbits and foxes, because when there are lots of rabbits, so there are more foods for the foxes. So the tendency is to decrease the population of the rabbits and the foxes to increase. And then a cycle will happen. At some point, there are so many foxes and not enough rabbit for their population. So the tendency is for the fox population to decrease, and then that's the time where the rabbit population will increase. Okay, so this is center at this point. So at the 0, 0, since it's both positive and negative, so the tendency is to circle. So there are arrows that will come in, arrows will come out. So probably that's the picture of this example, the pace portrait of this example. So that's all for this discussion. I hope to I hope I am able to explain what I am about to explain in this video. So thank you and have a nice day.